Okay, welcome everybody to this month's virtual CISL seminar. Glad you could join us. I'm Jeff de la Beaujardière, organizer of the seminar series. Our speaker today is Anissa Zacharias from NCAR, from the Technology Development Division. She's going to be speaking on GeoCAT and creating Python software for Big Data and HPC. Anissa is a software engineer at NCAR. She's a member of the GeoCAT team and works on computational and visualization tools for geoscience applications. She has a master's in computational science from Georgia Tech and a bachelor's in computational mathematics from Embry-Riddle Aeronautical University. She actually joined NCAR after the beginning of the pandemic, so I've never met her in person, but we've had a number of telecons as part of the Science at Scale project, and I'm very glad she agreed to give this talk on GeoCAT. So Anissa, if you're there, if you could unmute and turn on your screen and off you go. Oh, and sorry, I do want to add one thing. We're trying an experiment after the seminar, which is a Google Meet session, 30 minutes for quote unquote in person, a Q&A chat with Anissa, anything you'd like. So kind of like in the old days when we would step outside of the seminar room. So Tasia is going to put something in the Slido that tells you how to get yourself invited to that event if you're interested. So please do come along if you like, and we're going to try to have that going for future seminars. So Anissa, thanks again for speaking, and I'm going to shut up now and let you go.
All right, can anybody hear me? I'm going to assume so if nobody says anything.
I can hear you, that's for sure.
Okay, good. So my name is Anissa Zacharias, and this is a September seminar, CISL seminar called GeoCAT and Creating Python Software for Big Data and High-Performance Computing, a learning process. So here's a preview of what we're going to be up to today. We're going to go over who I am, which we've already done, but we'll do again, what the GeoCAT team is, what Science at a Scale is, and then we're going to look at the particular problem that has led us all to being here watching this presentation today, a little bit about high-performance computing and Dask, and then what our plan was and what actually happened. And next, we're going to go to doing some Dask, some details. And after that, we're going to do a short version of a development of one of the functions that we created for this project and how we use that function on Casper. And finally, we're going to wrap up with some lessons learned, an overall summary, and followed by some additional resources if you would like. Here's where I introduce myself for possibly the third time. So this is me. Here's some contact info if you want to follow up. Please don't send me angry emails. Nice emails are encouraged. I'm a software engineer at NCAR. I'm a member of the GeoCAT team, and I've been working here for just over a year. I have a bachelor's in computational mathematics and a master's in computational science, and I am not a Dask expert. I'm not even particularly good at the things I'm going to be talking about in this presentation, and I'm not an expert in any of this. This is going to be a learning journey of how I came to develop Python software at a scale using Dask. All right, so as we said, I think 4 times, I'm a member of the GeoCAT team. GeoCAT is the Geoscience Community Analysis Toolkit. It is a part of NCAR's Pivot to Python initiative and deals with open development, scalable analytics, and visualization tools for geoscience data. What we do basically is we are migrating NCL functionality over to the Python ecosystem, and we're hosting this on GitHub in an open development way so that everybody can contribute and see what we're up to, suggest what to do next, and a bunch of other cool things. Down below there's a link to the GeoCAT homepage where you can find more info about what we're doing, monthly updates, and links to our GitHub repositories if you want to learn more. Next, the next thing I need to talk about is Science at Scale. This is a program led by Jeff, who you just met, and it has the goals of establishing the capability to analyze large NCAR datasets in the public cloud, and also to demonstrate the use of NCAR developed tools such as GeoCAT on this system. And this is where my involvement in this project began. So the problem. This was November of 2020. I had been working at NCAR for approximately 4 months. I was a wee, young, freshly hired software engineer, and I imagine some of you have probably also experienced something like this. I found myself being asked from my boss to participate in a project in which I didn't really have any idea what was going on, but I was not going to admit that. So the project was to demonstrate GeoCAT's functionality on a large quantity of data in a high performance manner. And I thought, cool, no problem. At the time, I thought I was pretty good at supercomputers. I had done Fortran and C on supercomputers in my undergrad and grad. And I thought I was all right at it. And then I met Jupyter Hub on Casper. So we started on a journey comprised of mostly things I wasn't very good at, and that I'm now going to detail for your enjoyment. I mean, learning opportunity. But really, while I hope you do come away from this presentation with a better understanding of developing Python software for use with Dask, I also hope you can appreciate my perspective of a baby software engineer learning how to do something new and the development process that we went through on learning how to do functions with Dask in a way that we weren't totally familiar with. So first, a little primer on what parallel processing is. At the most basic level, parallel processing is doing multiple things at the same time, which is important when you have a bunch of stuff to do. So if you have a task, or in this case, something to distribute tasks, a task is then distributed to workers and then aggregated back to a common source. This is the most basic level of parallelism I could possibly explain. And we're going to get more into complicated versions later. So what does parallelism look like in Python? Honestly, it's a little rough and not recommended. And it doesn't work the same way that it may have in languages that you're more familiar with, like Fortran even, or C or Java. It's not a thing that you generally want to have to be dealing with. But here we are. So something has to work, right? There has to be some way to do parallel processing efficiently, somewhat efficiently in Python. That's where Dask comes in. So the next part of the problem is Dask. Dask is a flexible library for parallel computing in Python. You'll notice that Dask is listed in the problem part of this presentation, and this isn't a mistake. While Dask is an immensely powerful and useful tool, you need to be sure that you actually need to use it before getting into it. In the words of the Dask Twitter account, the first rule to using Dask, see if you can avoid using Dask first. If you're going on a small project with a relatively small amount of data and can get away with not needing to use Dask for anything, do it. There are easier and likely more efficient ways to speed up your code, and something even just like choosing better algorithms or using faster libraries like NumPy or Pandas can really be used before Dask. But here we are. For this project, we did need to use Dask. So here is the original execution of this plan. Our goal, again, was to demonstrate GeoCAT functionality at a scale. This part, as originally imagined, had 3 parts. The first was to be able to calculate relative humidity and dew point temperature. The second was to calculate heat index. And finally, the last one was to calculate potential evotranspiration. Each step on this process would be built on the previous, and they could all be theoretically developed in a sequence. But as good plans generally do, the actual process was vastly different from this, and it diverged almost immediately. So here's what actually happened. While the stated goal tied in with Science at a Scale project was to demonstrate GeoCAT functionality at a scale, in practice, the goal became how to write GeoCAT functionality that could work with Dask. This plan also kind of developed into 3 steps. The first was learning how to write Dask compatible functions. The second was learning how to use these functions on a distributed environment. And the last step was to write and rewrite these functions until the previous 2 steps actually worked, which is actually where most of the time in this project happened. Okay, so here's the part where we actually start to talk about Dask. If there are any Dask experts in the room, please forgive me. I, as we stated at the beginning, am definitely not a Dask expert, and this will be a abridged version, an overview of kind of the parts of Dask that we had to learn in order to get this project to work in a very short, compressed for a seminar version. I know for a fact that I cannot cover all of Dask, not only because we would run out of time, but I would run out of knowing what I was talking about very, very quickly. This is mostly going to be about how to write your own functions that work with Dask to be used by other people. It is not using other people's functions and using Dask on top of them, which seems like a very small, but is a very important difference. So keeping this in mind, let's get into it. Dask is made up of two main components, Dask collectors and Dask schedulers. Collections are extensions of interfaces that you've probably heard of, like NumPy and Pandas, that can interface with the distributed environment. Here they are, Dask array, Dask data frames, Dask bag, Dask array, and Dask futures. We will be mainly using data frames and arrays here. And schedulers are what allow these tasks to run in parallel, and it is the part of Dask that diverges from Python and allows things to be run in parallel better. And they're controlled through the task graph. So essentially you have Dask arrays, which form a task graph, which is then sent to schedulers. Please forgive me, Dask experts. That does parallel stuff. Good. What makes Dask truly useful and truly usable, though, is its reliance on familiar structures. Inside of a Dask array are familiar arrays, such as NumPy or X array. And X array is what we generally use in this project, but for here, I've demonstrated with NumPy arrays. With these, Dask allows us to use familiar tools on Dask arrays as if they were NumPy or X array arrays. There are limitations on this, however. Not all of NumPy's functions work well with Dask, and that's something we'll get into a bit later. But for now, this is generally what you need to know about Dask. You have Dask arrays, which you do stuff on that make task graphs, and it's handled by a scheduler, which makes it go in parallel good. And so now we're going to look at a function that we developed during the course of this project, how it works and how it changed as we learned more. This function is actually from the second step of the original plan, which is calculating heat index. This function was originally implemented in NCL, which is part of the reason why GeoCAT thought it would be a good idea to implement in Python specifically for this project. And our new Python implementation remains fairly faithful to the original NCL. The version of heat index I'm going to be showing you here is how it is calculated by the National Weather Service and is a slightly less complicated than the actual implementation, but serves as a really good example of what we did. So heat index, as many of you probably know, is a measure indicating the level of discomfort an average person is thought to experience as a result of the combined effects of the temperature and humidity of the air. Couldn't get through a presentation without Oxford Dictionary definition. And down below is a basic rundown of how the heat index is calculated. To start with, you have this function over here, which looks like some sort of estimation expansion using temperature and relative humidity with coefficients here and decreasing coefficients and increasing exponents here. So this is all pretty familiar. And then depending on both the outcome of this equation and the temperature and relative humidity inputs, there are a series of adjustments that we can go through. If relative humidity is less than 13 and temperature is between 80 and 112, we take this term right here and subtract it from the heat index that we've calculated. If relative humidity is greater than 85 and temperature is between 80 and 87, we take this term here and we add it to heat index. And if the heat index that we just calculated is less than 80, then we actually scrap this whole thing and we use this equation right here instead. Overall, it doesn't look too complicated to translate into a Python function. It's just fairly basic math. If you're familiar with NumPy and maybe the math package, it shouldn't take too long. Let's see. So this is the first pass at our development. I'm going to apologize for the next couple of slides. They are a bit of a jumble of code, but it's actually the blocks that are more important than the actual code itself. So just know this is exactly what we saw on the previous slide, just now in Python-ish pseudocode. So we have a function up here called heat index that takes two inputs, temperature and relative humidity. This right here is the equation from just before this one. And down here are our adjustments, exactly the same as before. We have heat index equals heat index minus and heat index equals heat index plus. and the adjustments, and here's where we scrap the whole thing and recalculate heat index of is less than 80. And then it spits heat index back out. So it looks a bit messy, but it's totally the same thing as before, now just kind of in code form. You'll notice that this slide is called first pass. The immediate thing that is wrong with this implementation, if you haven't thought of it already, is that it would work just fine if you passed in single values for temperature and relative humidity, as in like one-dimensional, like floats, or I guess ints maybe. But as soon as you try and pass an array through it, it won't work. If you haven't spotted it, it won't work because of these adjustments down here. This first part, totally fine. Python can handle this sort of computation with arrays. But if we go down here, if you see if relative humidity is an array, we can't compare things like this in Python and then have it also, well, we can't compare things like that in Python. But we also then say if like for specific indices in the calculated heat index, we would need to then find where relative humidity and temperature are both wrong and then be able to reference that value or that index in the resulting array, which this is simply not capable of. But as I mentioned before, Dask arrays are chunked into other arrays. So for a function designed to be Dask compatible, it needs to be able to handle multidimensional inputs. So after this first pass, we have a second pass. So this is, again, the same thing as before, just now even clunkier. This first bit, as I mentioned, is exactly the same. This part was totally fine with arrays. But now we've changed the adjustments, and now they're a lot uglier. But let's look at actually what we've changed. Using the where function here, we are able to make kind of an array, like a true or false array, a Boolean array, that selects where in the resulting array that we need to change heat index is why we're using it. We choose the conditions under which we need to change it with a NumPy logical and function. And it's essentially just logic that works on full arrays. So this is how we set it up. If we have a where function, a NumPy logical and of the conditions of relative humidity and temperature being between the right ones, and then we do the adjustment. And the way where works is you have kind of like a true or false kind of Boolean array, what to do if it's true, and then what to do if it's false. So the first part here is the condition. The second part here is the adjustment of what to put in place of heat index if it is true. And then our false condition is heat index itself, so no change. And then we do the same thing for the second condition. The third condition is a little bit simpler because we don't have as many conditionals. We only have one conditional, so we don't have to do any sort of logic functions. And then we spit it back out. So this handles arrays. It should be good, right? That's what I thought for a long time. However, this is still not optional for Dask, even though it does handle arrays. And unfortunately, that's because of the changes we just made, specifically those changes right there, all the NumPy functions in there, without actually NumPy square root. But all these functions right here, that's what makes this not Dask compatible. So this is because of what I mentioned before. Not all NumPy functionality will work with Dask. By using these specific functions, the NumPy where and the NumPy logical and, this is forcing Dask, when we're going to use it, it forces a serial computation and an immediate computation, meaning that when we're running the notebook, all the computation will have to stop and compute this before being able to move on. It won't be able to run it lazily, and it won't be able to run it in the background of the notebook that I'm going to show you, which defeats the entire purpose of using Dask. So how do we fix this? Fortunately, the change is relatively simple. The next slide will not be chunkier, I promise. That's it. That's the change. The change, as you can see here, is xArray. This is the last pass on the functions that we made. This is a simplified version of the heat index code that we're using now. And it's currently the way that we're writing Dask compatible functions. If you have any thoughts on this, please actually send me an email about it. Possibly there should be a fourth pass slide on this presentation. This is still a learning in progress progress. So thankfully, Xarray has functions that do not force an immediate compute and don't force serial computation. So when NumPy causes a hitch, thankfully we can use equivalent Xarray functions in some cases. And while I haven't mentioned much about Xarray during this presentation, it is our preferred package to use with Dask. In the notebook that I will show you in a minute, all of our inputs are actually Xarray whenever possible. So this is it. This is what we need. But it doesn't look like we're doing any Dask. And I know, for the most part, we leave the actual Dask handling to the user. So we don't force any sort of like method of computation, or we don't do anything that the user can't control with Dask inside of our functions. The first part of this was realizing that Dask compatible functions don't actually look like Dask, which is totally fine. But that's what we're going to do now. All right, so we survived, finished the Dask part of this presentation. Now we're going to talk about how we can use functions like the ones I just showed you with Dask. First, a disclaimer, there are multiple ways to run functions with Dask. This is just how we're doing it currently. We're going to use these functions on a Casper login node, which we will launch from a Dask, from which we will launch a Dask cluster. And finally, I know that doing big data on a Jupyter notebook might not be the obvious way to go about doing any of this, but the purpose of the project was always meant to be a demonstration for which Jupyter notebooks are annoyingly useful at. And so that's why we're doing it like this. Now we have to go back and talk about more Dask. Sorry. But this time for a more practical side. This is how we're connecting to a Dask cluster from a Casper login node, or at least one way. You can connect to a Casper, to a cluster other ways. I was doing it for a long time on this actual project. We are doing it from a Casper login node because it is relatively easy to have the NCAR job queue package launch a cluster for us, if that makes sense. And also the Casper login node is able to access the AWS lens data, which the compute cluster isn't sometimes. And so that's why it is set up like this. So as I mentioned, we're using a package called NCAR job queue, which was developed by Anderson Benhiwe. I've linked to his project at the end of the presentation. And it explains more about how to use this. Basically, it just makes starting up a Dask cluster on NCAR resources much easier. It uses a personalized configuration file, which is all explained in the documentation. And once you have that, that file set up, it then, you don't have to do anything in the notebook itself. You don't have to put like your cost keys or whatever into like something that you're going to commit to the internet. You don't have to specify the same things over and over again. If you need to change anything, you just go change that configuration file. So mine is already set up. We make an NCAR cluster that is right here. And then we scale that cluster to whatever size you want. This scale right here will actually create like 20 workers, and it'll give us almost 1 terabyte of memory. And then we connect that client, or we connect a client to that cluster using Dask distributed, which I didn't show the import here. So then if we look at client, what we just created in this last line here, this is what it shows us. It shows us the client that we've created. It shows us it's in a Dask job queue on a PBS cluster. It's a cluster object, it has 20 workers, 40 threads, just the right amount of memory. You can scale this however you want. This is just the most consistent way I found of being able to get the resources easily. And the most important part of this is this bit right here, the Dask dashboard. I knew I was going to mess that up. So that's it. That's how you run a Dask compatible function. After this, you run this, and then that's it. But as you might guess by the remaining amount of slide on this slide, we're going to dig into this a little bit deeper. So this is the heat index function, the actual implemented one that we ran. And this is how you run it on the Jupyter notebook. This is the background of it. So heat index, our desired output. This is how we import the function we just created. Up above in this notebook, which I didn't want to show the whole thing during this presentation, is imported geocat.comp, which is where heat index is implemented as GC for GeoCAT. And then the inputs, which are here, temperature and relative humidity. So if you look at the temperature and relative humidity inputs, these are actually X-array data arrays, and they come chunked. I didn't actually do that chunking. It came pre-chunked when we loaded in the lens data, which was immensely useful. Not that hard to alter if you need to, but nice to have it anyway. So this thing is about 10 gigabytes. It has a shape here. It shows us the chunk size. It gives us some information and some attributes that we've assigned. Not in this notebook, but in the heat index function itself. And here's the relative humidity. Here's what it looks like. It looks pretty much the same, except for the metadata here. And this is what we're going to give heat index. So it's not actually that big, but so it's about like 20 gigabytes that we're giving this thing. And here is one of the last things that we figured out in this learning process is to call persist. So directly from the documentation, persist is important because Dask is lazy by default. It is a way of telling the cluster that it should start executing the computations that you have defined so far, and it should try to keep those results in memory. This is immensely important because loading it from memory is much faster than reloading it from disk or having it recompute. This persist right here is what allows further computations down to run faster, because this will still be fast to access and has generally sped up our whole process a whole bunch. And so while that is running, you should definitely check out the dashboard. Whenever you run anything with Dask, it is always nice to then pop over to the dashboard, which I showed you the link to in the client output below or before. So this lets you check out how things are going. It's a bit of getting used to staring at it, but it is immensely useful at like telling what's going on behind the scene. You can check on your workers, see if there are any memory issues, how tasks are being distributed, if anything's being hung up or not computing in parallel like it should. This was actually very useful. If something started like going slow or not like computing in the background, you could pull up the dashboard and see exactly what was causing the issue sometimes. And it's just overall an extremely useful tool that you definitely need to poke around with if you're going to develop with Dask. As you can see here, the workers that we have here, I think 20, that's probably 20, I hope so. And you can monitor their individual data usage. Each one has the ability to go up to about 40 gigabytes. And this is the memory stored for all of them together. It is extremely useful to know when you're going to hit this, the most possible memory stored, because if you do, everything kind of crashes and starts over, which is immensely hard to tell if that's happening just from the notebook itself, or it was immensely difficult for me to tell when that was happening from the notebook itself, I might want to say. Down here, it also shows us what is being executed. These are kind of like the behind the scenes things. Like we didn't tell it to do all these essentially, but it's like what Dask knows it has to do in order to get all of this computed. And it shows in the different workers here, I think 40 of them, and generally what they're doing at each time. You can hover over them and see what's going on, and just making sure there's not like a lot of lag or time like between passing things between the different workers, if that makes sense. Yeah, an extremely useful tool if you're going to be doing anything with Dask. All right, And I think I talked a lot faster than I meant to, but we'll have lots of time for questions. So this is miscellaneous best practices. I know I've talked vaguely about Dask a lot and about a couple very specific Dask things, but just to give you kind of an overview of general lessons that we learned along the way that didn't fit very well into this presentation. Avoid using Dask if possible. Please try to use better algorithms, data structures, especially for small problems. If you're going to have a bunch of workers working on a problem, there's a lot more overhead and a lot more pain and suffering in trying to get Dask set up properly than would be to actually just do it the hard way. Especially if the amount of overhead from setting up and running your workers is going to be more costly than just doing the computation. The second one is avoid making chunks too large to fit in a single worker's memory. This is also something that we ran into as it tried to load in the data from the chunk or from the lens data. The pre-computed chunk size would often overwhelm a single worker's memory and would cause the entire thing to crash. Even if you don't think you're close to a terabyte of data, sometimes you do based on just how the data gets distributed between the workers. And if you can, keep things in memory that you intend to use again. This is what I was talking about with the persist. It is extremely useful if you have the data or if you have the space available to keep the things that you've spent a lot of time computing easy to access. Also with this, I would like to mention, it's probably not best practices, which is why I didn't get its own bullet point, but I found that saving out intermediate results is useful. Probably not the best thing to do, but if you're going to be experimenting on a notebook and say you have 2 hours wall time and you hit that 2 hours and you have to recompute everything every time, seems a little wasteful and took a lot of time. My development work got a lot faster once I learned how to output the data properly and then be able to read the data back in, not to the login node, but to the worker's memory directly. You can see all this in the linked notebook that's going to be at the end of this that shows the entire process and the actual 3 scenario structure that originally got laid out. And you can see a lot more detail of what we did there. And ensure that you're not actually using functions that force computation. Some of the functions that you don't think would force computation actually do, and some of them that you think might probably don't. For example, before I mentioned that we were able to use NumPy square root function, totally perfectly fine. But NumPy where absolutely forced things to go serial, which was confusing to figure out and had to be tested kind of individually. I know there's documentation that says like exactly what is, but on the fly, it is always good to keep check that what you're doing isn't either forcing serialization or forcing computation. And lastly, avoiding calling compute when not necessary. While Dask, it does compute lazily, you will have a bunch of things that aren't computed that are only computed when called on, or are called like in the background. For example, like when persist, it tells it to start computing in the background, converting it from something that just is kind of sitting there knowing it has to be computed. But avoid calling compute directly, like as in .compute, because oftentimes it isn't needed. When you call .compute on a certain function, it forces it to start immediately. And often the Dask backends, it can simplify things, if that makes sense. If you let Dask do what Dask thinks it has to do, this can lead to some funny results. Like you think you have everything computed and then you call like plot and it takes like an hour for the plot to show up. But for real, if you can avoid calling compute, just let it do its thing. And if you like stack several operations on top of each other, a lot of times the task graphs which I was talking about can simplify on the back end kind of as much as Dask can figure out how to do. There are ways to like figure out how to optimize task graphs, but that is super beyond my knowledge of doing this. And so simply avoid calling compute when not necessary. And so we've done it. Here's the summary. I hope you enjoyed this presentation. here we went over an overview of GeoCAT, science at scale, and a peek into what DAS can do, or a peek into what I think DAS can do. I showed you roughly one way to write DAS compatible functions, create functions that are compatible, are DAS compatible internal functions, and implement the functions that you have created on a DAS cluster, and a touch on some of DAS best practices for development and usage, and a story of development, errors, and hopefully some funny misadventures. I apologize if this presentation seemed funny. There was way too much of way too many things to fit in. I tried to get kind of like a sampling of a lot of things. And that's it, folks. We've done it. Here is a list of some resources for you to check out. Some DAS documentation, best practices, some like deeper information of some of the things I only kind of grazed over, a couple of great tutorials that helped me get started. Of course, a link to Project Pythia's Python tutorial series, which touches a little bit on Dask and Xarray, and the package that I mentioned of Anderson's NCAR job GitHub. All right, thank you for your time and attention.
Great. Anissa, thank you very much for your work on GeoCAT and our Science at Scale project, but also for your very frank and informative talk. I hadn't realized we were kind of throwing you to the wolves, or maybe that's not the quite phrase, but like throwing into the deep end of the pool. Maybe that would be a better metaphor when you started working on this. So looks like we do have a couple of questions. So what I'm going to do is read them out, and then you can answer them. And I do just want to remind people, do we still have, no, I guess Tasia does not anymore have the question about, oh yes, there is. No, the poll, never mind. Sorry, I was just trying to see if the question about, do you want to join the after seminar? Yes, it is, it's in the poll. If you go to the poll and type your email address, if you would like to join the after seminar chat session. Okay, so coming back now to the questions. Let's see, Paul, can you put them back on screen here? All right, first question from Thomas. Are there plans to fix NumPy functionality to work with Dask?
Yeah, actually, not by anything that GeoCAT is doing, or I personally am doing. But from what I saw during the documentation, partially in prep for this presentation, is that there is plans to incorporate more of NumPy's like interfaces, especially like the linear algebra part of NumPy, in like to be compatible with Dask. If you want to get into like the gritty details of why it doesn't, there's a resource I linked about the global interpreter lock, and it just has to do with the way like Python tries to do things in parallel. Essentially, NumPy uses this, it like interfaces with the global interpreter lock of Python, which only allows one thing to be done at a time. I apologize if I'm kind of like messing this up, but from my understanding, the global interpreter lock allows things to be done like concurrently, but not in parallel, if that makes sense. And a lot of NumPy uses it internally, so it's hard to make Dask do good with it, if that makes sense.
Great, thank you very much, Thomas. I hope that answers your question. Next question by JC. Oh, hold on, the order. Oh yeah, here we go. JC, can you talk about any performance speed up over the original serial implementation?
Yeah, so I don't have any actual numbers for you, but I do know that at the beginning of this, I did calculate a rough estimate of how long this entire thing would take to compute in serial, or at least part of it. And I believe it was somewhere around 36 hours, which eventually got sped up to around 15 minutes when properly implementing all the parallel capabilities and massively scaling up the number of resources I was using, and also making sure nothing was computing in serial that secretly wasn't supposed to be. But yeah, you can get things done a lot faster when you have kind of like a terabyte of workers doing everything for you. Even with like some smaller versions of the cluster that I was doing it just so I had like basically just bigger than the amount of data I was doing, which also caused some issues because it would crash a lot. But it would take it would take a very long time. It was very difficult to test because every time I wanted to run something, it would take just like a couple of hours of me sitting around. I don't know if that answers your actual question, but if you can, use a sufficient amount of resources to get optimal speed up for using things like Dask.
Well, certainly going from tens of minutes to tens of seconds sounds like a great amount of speed up. So
yes, it was great to learn that I could run things in 15 minutes instead of taking all day to compute the whole notebook.
yeah. Okay, looks like next question is from Anderson. Great talk. What do you find most challenging / frustrating about Dask?
Hi, Anderson. Honestly, the documentation. There is a bunch of documentation, but I didn't find that there was a clear how to start for different approaches, if that makes sense. There's a lot of how to do various things in Dask, but not kind of like a how to for, like, say you have a function that you didn't write and then how to use it. That was fairly easy to find, but how to develop a function to work with Dask that then you could use is an entirely different how to use Dask situation. Also, I know that it's kind of like changing because I know there were several updates while I was doing this project, but just how to get started was kind of hard. It was hard to figure out where to start. It was hard to figure out what kind of computes or persists I could be calling. A lot of things were frustrating. And I think most of it comes down to there wasn't a clear roadmap of what to do, what, and when.
Okay, thank you for that answer. Next question by Anonymous. Is every Xarray function Dask compatible? Is there an easy way to tell whether a function is Dask compatible without just experimenting?
I'm not sure if every Xarray function is Dask compatible. I know that Xarray does work, like the developers of Xarray and Dask work together, I am pretty sure. And so Xarray is a lot more Dask friendly because Xarray is developed with Dask in mind, if I'm not wrong, where NumPy isn't. Is there an easier way to tell whether a function is Dask compatible? That was almost a part of this presentation. And the answer is, I'm not sure. I thought there was. Anderson, if you're around, and maybe during like the second part of this, I would love to know. Anderson, you taught me a way of doing it like on the fly, of basically having like a really small like array of like 10 elements. And we took it and we chunked it, we turned it into like a Dask array, and then we passed it through and we see if it force computed into like, if we pass it through and we see if it force computed it essentially, except for I thought that would do it because if it's not forced computing, it should be fine. But during the last stage of the development, actually something that we figured out like a couple of weeks ago, our heat index, the function that I showed here, it broke. And somehow, I think it was like a developer error. It was definitely a developer error. But some NumPy functions, the ones I show you, they snuck back in after I swear I had removed them. And the tests that I wrote some tests that like it had a really small thing and it passed it through and to see if it force computed it. And it was passing those tests, but it was absolutely still running in serial on the cluster. So for now, again, I'm not an expert, but I don't know if there's an easy way to tell.
Okay, well, thank you for that insight. I mean, it shows that the problem is actually kind of complicated. Next question by David John Gagne. What experience have you had, if any, with using Numba to accelerate GeoCAT functions? Numba, I'm not sure how to pronounce that. I haven't heard of it. N-U-M-B-A.
Not gonna lie, none at all. I'm not sure if other members of the GeoCAT team have, but I have no experience using Numba whatsoever. I think, actually, I'm pretty sure that since I've been on the team, this is the first kind of like speed up using like parallel stuff that we've tried.
Okay. Looks like there's two more questions really by me. and then we'll give Tasia's reminder at the end. So all of the conference talks I've heard make Dask and the various Python tools seem easy to use. You know, everybody's up there, they're showing their PowerPoint. Yeah, we did this, and they flash up a graph. Sometimes they actually, you know, launch their Jupyter notebook during the talk, and at the end, well, magically it's done. Makes it all seem very easy. You're pointing out that sometimes it's not that easy and doesn't always work. But would you say overall that the new Python-based GeoCAT will nevertheless be easier for future users than the old NCL? I mean, there's bound to be a learning curve for both, but is it good that we've gone to Python? Is it overall going to be easier despite some of these hurdles?
Oh, absolutely. It's also good to note that some of this making Dask compatible is a really good goal, but it is also, you don't need to have Dask compatibility to make good GeoCAT functions, in my personal opinion. My boss might not agree with me, but in my opinion. Python is actually not my favorite language to use, but I think just the overall familiarity that a lot of people who aren't necessarily software engineers have with Python, and the environment that it creates where everybody can make packages, you know, fairly easily and be able to use everybody else's code, and just the low barrier to entry, I think will make Python a really good alternative, especially to NCL, which before I started interviewing for this job, I'd never heard of. And I was moderately familiar with tools for like geoscience applications in like the coding realms. And so I know NCL is useful, it's extremely useful, but just to be able to get things out in a way that has such a low barrier to entry, I think is a major advantage. And also, I would like to say that the functions that we've created for this, the heat index, the relative humidity, all of this, you don't have to use Dask with them. Internally, they actually have kind of like a switch for if you pass in something that's like a chunked X or a Dask chunked anything, it will kind of siphon you off to what is Dask compatible, and which of course has a little bit more overhead than everything else, just because of all the different stuff you have to do that you wouldn't necessarily have to do if you're just using like straight up NumPy arrays or just lists or anything. And so, yeah, it's definitely harder from a development standpoint to make everything like perfect and Dask compatible, but from a user standpoint, this should be pretty easy to use.
Excellent. I'm going to jump down to Thomas's question, which actually just came up. I guess based on what you were just saying, what is your favorite programming language?
This won't be a popular answer, but I was taught Fortran. I am a huge Fortran nerd. I like that you're able to control everything. I learned how to use supercomputers on Fortran, and I knew exactly what was happening and where to look for what. It was fantastic. Also a big fan of Java. C is fine. I don't want to start language drama, but Python's all right. It's better than C.
All right. Yeah. Let the religious wars begin in the post-seminar chat room.
Not sure what drama I just started.
Well, I mean, you're in the right. If you look like Fortran, you're in the right place, right? NCAR is, you know, a good place for that. Okay. So one more question looks like, and this one is also for me. You said earlier that the pre-computed chunk size for the lens data that we had put on Amazon and on the NCAR object store, that the chunk size was sometimes too large. Would you recommend that we reconfigure the ZAR stores into smaller chunks? Because that's something we can actually do without it would be an under the hood change and just rechunk everything a little smaller without changing things at a higher level.
No. I think that was mostly my bad of not realizing that the chunk sizes was overwhelming the workers. But specifically, I think not like on the back end, but users need to make sure that the chunk sizes they're using will not overwhelm the worker memory, which is not something I necessarily like thought of while developing this for a really long time. I think the chunk sizes are fine for the size of the data. Just using enough resources and having the guts to request a terabyte of memory on something was mainly the hurdle.
Okay, I think when we did the chunking, we had tried to strive for about 100 megabytes per chunk, roughly. So, which meant maybe 50 to 200 overall. I guess.
I would also like to say, like, users can rechunk it. It's fairly trivial to rechunk something.
Okay. Okay, so two more sort of comments, one by JC, long live Fortran. And then Tasia reminds us, if you'd like to attend the after seminar chat session with the speaker, please submit your email as a question, I guess, in this Slido, and I will add you to the event. Do not reply here, otherwise your email will be public. Thanks. So Anissa, thank you very much for your talk. I think we're going to go ahead and, since we're out of questions here, we'll go ahead and start the Google Meet after seminar session right now instead of waiting to the scheduled 2 p.m. time. And so hope to see a number of you there. Thanks for attending. If you would like to be a speaker in this series, please let me know. We have numerous slots open, so love to hear about your work, or even have suggestions of people outside of NCAR that you would like to see speak. So Anissa, thanks again very much. Paul and Tasia behind the scenes, thank you for helping run all this, and everybody have a great afternoon.